Hi, in this video, we want to take a look at principal component analysis and the extensions. So here, we're going to take a look at PCA, and principal component analysis kind of lives in like two worlds in a way. One side, it's very useful for things like machine learning. Other side, it's useful in like latent variable analysis. And so when we're dealing with it, we actually get like two aspects of the same thing. And both of them are right, both of them are good, but both of them are very different for our utility depending on the project that we're on. Now, we're going to run through some examples from Modern Psychometrics with R by Mayer, and here's the GitHub page to get the code that I modified for this example. All right, so principal component analysis, I would say there's probably four major uses of it. So the first two are usually more like machine learning, data mining uses. And we're going to say dimension reduction and transform data into uncorrelated columns. Okay, so dimension reduction, the idea is maybe I have thousands of columns of data, and I know that if I use all of those columns, I'm going to overfit my model, if I'm doing supervised learning, that is. All right, so what I can do, instead of using my original data, I can use just a few principal components, and that does a pretty good representation of the informative value of the entire data set. All right, so that is the dimension reduction use, is that basically I just want fewer columns of data, but I don't want to suffer a huge information value loss. Now, the other way that we can go, and this is really along the same line as dimension reduction, just with more columns, is I want to transform the data into uncorrelated columns. All right, this is usually used in situations like I'm using like neural networks, maybe for image processing or video processing or sound recordings that are being put into a machine learning algorithm. A lot of the algorithms, a lot of the neural networks perform better if they have perpendicular vectors going in. So doing this using principal components can give me that very nicely. Now, the next two are really more of a psychometrics point of view. So the first one is I have factor analysis. I want to do latent variable analysis. So why would I do this? I believe that there is some under the hood, hidden, unobservable, latent variable that's driving the data that I have. And I want to see, I want to get an idea of what those under the hood hidden variables are and what are the relationships to the data that I do have. So that would be our factor analysis example. Now, in IM response theory, what this does is it takes the factors from factor analysis and then applies those to the data set that generated the factors, and uses that to analyze the data themselves. All right, so let's look at an example. So here we're going to do pseudo-random number generation, and I'm going to just generate an example with 3 columns, pretty simple, just so that we can get a feel for what does principal component analysis look like. All right, so what I'm going to do, I'm going to do multivariate normal. So I'm going to have, this is going to be a 3-variable multivariate normal. And if you know anything about multivariate normal, all right, I have to give the center vector and I have to give the covariance matrix. That's all I need to be able to have a distribution for multivariate normal. Okay, so for this example, we're going to go ahead and say that the center vector is all zeros. So our data is centered at the origin. It makes it easy. Now, for my covariance matrix, I'm going to go ahead and define that with this matrix right here. So you can see that with this matrix, I have 2.8.8.5. Okay, so here, oh, and then I have a 0.1. This is saying that the variance of column 1 is 2. The variance of column 2 is 0.5. The variance of column 3 is 0.1. Now, the off-diagonal entries are the covariances. So we know that column 1 and column 2 have a covariance, not correlation, covariance. They're related, but they're different. There's a covariance of 0.8. Now, I have a covariance of 0 between column 1 and column 3. I have a covariance of 0 between column 2 and column 3. So this means that they're not correlated. Okay. All right, so now I'm going to generate my data. So here I'm telling what the central tendency is. So I'm just saying the origin. And I could use any three values I want potentially. I'm going to say that covariance I just talked about, my covariance matrix. And now I'm going to generate the entire data using the MVT norm package. And I convert it to a data frame. That way I can work with it with more functions within R. So this as.data frame, the reason why I'm doing this is because the initial data is generated in matrix, and matrix isn't always usable by all functions. So to give myself the utility of a data frame, I use as.data.frame. Easy peasy lemon squeezy. All right, so now let's go and let's look at the pairs of it. All right, so let's look at this. I noticed that I have a line there, huh? Well, that, you know, there's a slope here. Now, the picture here and the picture here, these are transposes of each other. So, you know, if I take my X and Y coordinates and I switch them, I'll get the same picture. There's just that like weird reflection aspect. This picture and this picture are reflections of each other. This picture and this picture are reflections of each other. It's hard to see because of the rectangular shape of the plot in our markdown, but it's that way if you start really looking at the axes as well. All right, so you'll notice that this just looks like an ellipse floating in space. This looks like an ellipse. That's because there's zero correlation between column 3 and the other two. Now here I notice that there is a slope going on, and that's because we have that covariance that we defined in sigma. All right, so now let's take a look at singular value decomposition. Okay, so singular value decomposition. Anytime I have a numeric matrix, I can do singular value decomposition. What it does, it takes the matrix I have, and you can think of it as it factors it, but it does matrix factorization, not number factorization. They're similar, but different, once again. All right, so what it's going to be is that the original matrix is equal to U times D times the transpose of V. Okay, now this doesn't seem like a whole heck of a lot, but this is powerful stuff. All right, U is going to be an orthonormal matrix. We call these the left singular vectors. All right, so this is going to correspond to my transform data when I use principal components. It's not quite that, but it's close. D is the diagonal matrix of the singular values. So this is how we get the standard deviations of the overall data that we'll look at in a moment. And V is the orthogonal matrix. So the right singular vectors. This is where we get our loadings. Okay, so now the author of the textbook called our data set a baguette. Why does he call it baguette? Because he looks at this part and he goes, oh, wow, that looks like, that looks long and that looks pretty narrow. That looks pretty narrow. It looks like a baguette. I don't know if I really buy it, but whatever. I don't have the urge to eat a baguette right now. All right, so let's take a look at the singular value decomposition. All right, how it stores a D, a U, and a V. Now, when I do the decomposition, it's always U times D times transpose of V. That's how the matrix is equal to U times D times transpose of V. But that's not the order that's saved in R, which is fine, but we just be mindful of it. So D, this is where we're going to get our standard deviations in a moment. It's not quite there yet, but it will be. All right, this is where we'll get our principal components is from U, and our loadings will come from V. All right, so let's take a look at the head of U. All right, so the number of so when I do this, if I do the full decomposition, I will have as many rows in U as I have the original data. I'll have as many columns in U as, excuse me, I will have so I will have as many columns as I have for the original data numerically. If I'm talking about theoretical, I can extend that to be an n by n orthonormal matrix, a basis, in fact. We don't need to worry about that in this case. Now, our singular values, D, in the matrix multiplication, that's going to be on a diagonal matrix. And here is that diagonal matrix right here. And V is the right orthonormal matrix in the factorization. And this is where we get our loadings. All right, so now I want to demonstrate to you that the vectors from U and V are orthonormal. That is, they are perpendicular to each other and they have length 1. All right, so you'll notice if I take any two columns of V and I multiply them using a dot product, so that I multiply and add, multiply entry-wise, add the results, I get 0. Now that's within machine accuracy of 0. Something about computers, remember computers have a finite amount of memory. There is always a round-off error going on, even if you don't see it. Now, if I take the length of a vector, so remember the length of the vector is all the entries squared, add that up, take the square root. It's the Euclidean norm. You'll notice I get length 1. If I do it again for another vector, I get length 1. Now, if I take an orthonormal matrix, transpose, multiply by itself, then what I'm going to see is I'm going to get the identity matrix. So you'll see that I have 1, 1, and 1 on the diagonal, and everything else are zeros or within machine accuracy of 0. So, this -17 scientific notation, there are like 16 zeros, a point, 16 zeros, and then a 1. If I was to write this out, that's so close to 0, we just call it 0 for all practical purposes. This is because of numerical inaccuracy with the machine. You're never going to beat this. This is close enough for any real application. All right, so now what we can do, we can take a look at the 3D plot of our data, because remember I have 3 columns. And after I do that, I can put on arrows showing me where the principal components are pointing. Okay, well, when I do that, in R, I get plot 3D. I'm using the RGL package. And what this will do, this will open up a GUI so that with your cursor, you can start moving around the cloud of data and you can look and see what's going on. Now, our Markdown generates static documents, so I can't put an interactive figure on there for you. So I just didn't do it. The code runs. It worked on my machine. It was beautiful. And this part of the code plots the points. This part of the code puts arrows in the direction of our loading vectors. Now, I told you that the matrix is equal to U times D times transpose V, right? Well, I'm going to prove that to you right here, right now. I'm going to take the original data. I'm going to subtract U times D times transpose V. Now, this is an entire data matrix. So this is, this has 1,000 rows, 3 columns. It's a lot to look at. So what I'm going to do, I'm going to apply the Frobenius norm just to prove to you that it's in fact, they're equal to each other up to machine accuracy. So the Frobenius norm squares every single value, then adds all of it up, then take the square root. It's similar to the 2 norm. All right, so when this does this, so I'm taking original data, I'm taking the product of the factors, and I'm subtracting. Okay, so if I had a perfect machine, every entry would be 0. It's not a perfect machine, so it's not quite 0, but it's pretty darn close. Then what this step does, this takes the data, squares every single value, adds all of them up, and then takes the square root. Okay, a lot going on there. But since I squared everything, every single number in that addition is positive. And so if I get the end result is close to 0, I know every single time we had subtraction, the subtraction result was close to 0. And boom, we get something e to the -14. So it's 0.13 zeros, then the number 2. That's pretty small. Especially considering there are 3,000 numbers being squared, then added up, square root. That's teeny tiny, teeny tiny. All right, so now there are 2 ways to compute principal components. One is using singular values and one is using eigenvalues of a covariance matrix. All right, so here what we want to do is we want to pull out the connection between the singular values of covariance eigenvalues. So what I'm going to do So here I want to demonstrate that the connection between eigenvalues and singular values. They're related but different. All right, so I'm going to take the covariance of my data set. And here is the covariance. Now you'll notice it's very close to sigma. It's not quite sigma because remember we did random number generation. So if I, instead of 1,000 entries, I would have had 1,000,000. It would be even closer to sigma, but it's not quite. But here we can compare the two, and they're pretty close. Not perfect, but close. Now, if I take the eigenvalues of that covariance matrix, here, the one that is coming from the data, I can see that I get my decomposition, or eigenvalue decomposition. Here are the eigenvalues. And here I get the loading vectors. Okay. Or something related to it, I should say. Now, if I go through and I take the d from the singular value decomposition, divide by n-2, take it inside the square root, and I square everything. So this will be the singular value squared divided by n-1, I get exactly the same values I have for the eigenvalues. So what this is telling me is that the singular values are coming from eigenvalues of the covariance matrix. All right, so let's go ahead and let's do this on a real data set. And let's work on computations of principal component analysis. Let's use the Brain IQ data set from the MPsychoR package. And check out this data here. I can see that I have some values, and this is a much different scale of numbers. These are much bigger, right? Okay. So when I do principal component analysis, what's going on is I'm going to go ahead and run printcomp. All right, so this is using eigenvalue decomposition instead of singular values. This is actually the weaker way to go if I'm talking about numerical stability. But this is a better supported version if you're doing things like factor analysis. So we have this contradiction going on. There is a correspondence between the two, but there is a difference. You have to have kind of like wonky cases for it to really matter, though. So it usually don't worry about it, which one you pick. Now here I'm saying use correlation instead of covariance. And so here I get my standard deviations. Here I get my loadings. And now, we can see the sum of squares of my loading here. You can see these are all the same. And they, since they're all the same because of the core equals true aspect, we have, equal proportion of the variance. Now, if I do the eigenvalue decomposition, I see that I have 2.03, 0.25, and 0.22, and then I get these vectors. And you'll notice the vectors are very close to the vectors here. That's not a coincidence. So the loadings and the eigenvalue vectors are very similar because they are the same, at least mathematically. Numerically, there'll be some differences. Now, if I take the square root of these values, if I take the square root here, this 1.43, 0.86, 0.47, you'll notice that's the same values I have up here. So if I wanted to, I could manually compute this using eigenvalues, or I could just let the function do it itself, which is the better way. And here I get those vectors again. Now you'll notice if I take the eigenvalues and I divide them by the sum of the eigenvalues, I'll get 0.68, 0.25, 0.07, and you'll notice I get exactly the same values here. So this tells, this gives me a representation of the the amount of variance accounted for by one particular vector. Now, we can do the same thing using singular values. So previously, we took the eigenvalues of the covariance matrix. If I want a better way to approach this, I can go with singular value decomposition, and it's numerically better because there are problems with eigenvalues. When eigenvalues get close to 0, you can have issues. All right, so here in R, I have two ways of computing principal components. PRIN comp uses the eigenvalue decomposition. That's better supported for inference. PR comp uses singular value decomposition and is numerically more stable. You have to make your choice on which one you want to use. Vast majority of the time, it doesn't matter. As long as you have full rank, and I don't mean it, as long as you have full rank data and correlation isn't a huge issue between your columns, you can use either one and it won't make a difference. If there is, questions on it, if you feel like you have a near linear dependence between vectors, you want to use PR comp. And here we can see we get the same standard deviations. Now, we will get different values for our rotations up to a negative sign. So we can, if I see a +1 or a -1 multiplication, it's okay. Because it's the same, it's kind of like if I'm pointed this way, my arrow in one sense is also pointing backwards, pointing in both directions. Where it's coming from and where it's going, just that if it's negative sign, it's like it flipped it that way. Now, if I want to get the singular values, or sorry, if I want to get the variance aspect, what I can do is I can just do singular value decomposition on the rescaled version, and boom, I've got my singular values. And we see the same matrix again. Now the X, this is my principal components that are coming up. So if I wanted to do dimension reduction, or I wanted to replace my data with perpendicular data, then this is the data that I would be replacing it with. And now here is another way to get these principal components, is that I can manually take that U, I can manually take the singular values and compute it myself manually. Don't compute it manually, let the machine do it. All right, so now let's take a look at some practical issues on principal component analysis. All right, so something that we always need to be thinking about if I'm doing dimension reductions or factor analysis is how many principal components or factors to use, how many to call. All right, the scree plot gives me an idea. All right, so there's a couple different standards. First one is if the singular value is greater than 1, then I want to keep it, or possibly equal to 1, depending on who you're talking to. So here is that line of 1. So that would say go with 3. Now, another way to go is I want to go until I hit diminishing returns. So diminishing returns, by my eyes, is at 4. So you see that it flattens out here. All right, so that tells me, like, if going with 5 is not a huge increase over 4 for the amount of complexity that I'm adding to my model. Going from, if I go with all 10, you notice that there's not much of an increase over 4, by this plot. So therefore, I feel like maybe 4, possibly 5, definitely no more than 5 because of how flat this is right here. The idea is I want to look for like elbows. Well, when you look for elbows, you notice that that looks like an elbow. So it would be reasonable to go with 2 on this. Honestly, you could go with 1. This is a very subjective criteria. Another one is to go for the amount of proportional variance accounted for. Very reasonable if there's a standard within your office or for your project. Another one is to go whenever the eigenvalues are at least 1. And so that the line is here. I already talked about that. All right, so now we can look at our rotation. And so the rotation matrix it tells me what the loadings are, how important is each item inside each of the principal components. And so we can see that, like in the first one, I notice that I've got large value, I've got negative values here, and I've got positive values here. So when I want to interpret this, I want to start with the biggest magnitude, then the second biggest magnitude, then the third biggest, and so on, until I feel like I know what's going on. And so here, I would, so because these are all bigger than all of these in PC1, I would say that this is capturing someone's approval of the positive aspects of the privacy. Now down here on PC2, since these are larger here, this is primarily picking up on the disadvantages of privacy. And now the third one is going to be generating kind of like a more nuanced contrast. So how I look at this when I interpret it, so always look at the big values first. And basically, you look at the big values first, and then after a certain threshold, you just ignore the rest. I see 0.4, 0.4, 0.4, 0.4. So I see, and you notice that these are negative. These two are negative. These two are positive, and they're the biggest ones. And I'll go ahead and throw these two in since these are still the bigger ones. I feel like PC3 is detecting the differences between the positive aspects of privacy. So some people are going to put some emphasis on these positive aspects more than these others, and PC3 is detecting that difference. All right, so now let's take a look at the biplot. So here, what this does, this plots the two principal components for each individual data point, and then it shows us the where the loadings are on each of these. And we can see that all the positive ones are together, all the negative ones are together. Now, another interpretation of the first principal component, because positive and negative are splitting, this could be detecting that one. But I think because of the size, I'm going to go with my first conclusion. Now, there is a difference between principal component analysis and exploratory factor analysis. Okay, so you can think of principal component analysis for the purpose of factor analysis is like the simplest, most basic version of factor analysis. Okay, so what is the difference? Well, first and foremost, when I'm doing the fitting, exploratory factor analysis is more concerned with the covariance terms than the variance. Principal component analysis puts more of an emphasis on the variance. Now, they don't ignore the whole, they don't ignore the other. They just, where do they put more of an emphasis? Factor analysis puts more of an, exploratory factor analysis puts more emphasis on the covariance in the covariance matrix, while principal component analysis puts more emphasis on the variance in the covariance matrix. Another difference is that exploratory factor analysis is statistical with like a geometric foundation, while principal component analysis is strictly geometric algebraic. All right, so exploratory factor analysis since it takes error into account, it has an error term in there. So we accept the fact that our data is not perfect. Anytime I'm doing principal component analysis, my model truly is assuming that I have perfect measurements, which is absurd for the field that we're talking about. Now, something that is nice is that since there is a connection between geometry and algebra, this is a nice presentation or nice connection to algebraic topology for all of you math people out there. It's a beautiful field, it's wonderful, but I'm not doing videos on algebraic topology. Something that is different between the two is that exploratory factor analysis, I need to declare the number of factors I'm using before I do the fitting. Now, that's not true all the time, but just think that I need to declare it beforehand. Something about principal component analysis is that if I go 5 or if I go 10, the first 5 will be the same as the first 5 in the 10 up to a negative sign switch. So it doesn't matter like how many I compute, I get the same vectors every single time. In exploratory factor analysis, if I change up the number that I want, I will get different vectors. Exploratory factor analysis, the factors are not orthogonal most of the time, and principal component analysis has orthonormal factors every single time by construction, by the geometric way that it's built up. All right, so now let's go ahead and take a look at some factor analysis. So what we're going to do is we're going to go through and I'm going to do principal. I'm going to use the principal function to get 3 factors, and I'm not going to do a rotation. And so now I can get my loadings off of that. And so now I have the loadings. Now here, you'll notice I've got bigger values on those positives. And so this kind of stands out more. You'll notice also in PC3, these numbers have been dropped out because they're not as important. So this is saying that like PC3 here, it's easier to interpret because the other values have been dropped. When I do factor analysis, exploratory factor analysis, it's easier to interpret the loadings because it's designed that way. It's designed to make it easier for me. Now you'll notice that as I'm working through this, the proportion of variance that's accounted for will change because in exploratory factor analysis, it's not designed to pick up the maximum possible variance. Now, when I look at the Varimax rotation, I see that my loadings have changed. Now, so here I can see the different loadings, and you'll notice that these have changed quite a bit. Oh, actually, no, it moved RC3 over. So the one that I was talking about has been moved over. And so this should be easier to interpret if I take the time to dig into it. But you'll notice that the proportional variance is going to be less. And now here I can use Promax. So these are the 3 major ways that we usually do factor analysis of no rotation, Varimax, and Promax. There are dozens of ways to go about it, but these are the big heavy hitters. And you'll notice that my loadings have changed because of that rotation aspect. Well, that's all I've got for you. Take care and goodbye.